Hello everyone. Today I want to give a brief introduction to what linear algebra is all about. This is material from 1.1 of the text. So if you ask me what linear algebra is about, I can kind of give you a one-sentence answer. So linear algebra, I guess in a nutshell, is about solving what are called systems of linear equations. Okay, so that's the one-sentence answer. Now, there's a lot to unpack here. What do these things mean? Well, what is a linear equation? A linear equation, this is something you've probably seen before. So let's say in variables, a linear equation comes with variables. Let me call them x1, x2 through xn. So you might be used to, x and y as variables. We want to deal with arbitrarily many, so I'm going to call them x1, x2 through xn. And so what is a linear equation? Well, it's an equation of kind of the simplest form. So of the form, let's say a1x1 plus a2x2 plus dot 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 plus an(xn) equals something equals b. So what am I saying here? Well, the x1, x2 up through xn, those are the variables, those are the unknowns. So these ai's, these will be numbers where each ai is a real number. These have a name, these are called the coefficients. And then, the coefficients are the things we put in front of the x's, and then b itself should also be a real number. Okay, so these can be any real number, an integer or otherwise. So let me give you maybe an example of what I'm talking about here. So again, these are the simplest kind of things you can do. So I'm going to put some number in front of x1, say, some number in front of x2, maybe 0 in front of x3, 0 in front of x4. So then I'll have an x5 minus 4x6 equals something, let's say pi. That's a linear equation. What's not linear, right, is if you, either start having powers of these variables or the variables multiply together. So for instance, something like that is not allowed because I have x2 times x3, or, a power of one of the variables. This is not linear. That's not allowed. Okay, so linear equations only have the variables raised to the first degree with possibly a number in front of them. So that's a linear equation. What's a system of linear equations? Well, that's kind of easy. It's just the collection of such things. So a system of linear equations, it's a collection of linear equations. Okay, so it's just a bunch of these things kind of considered at once. So maybe an example here that we'll come back to later is going to be, for example, let's say x1 minus 2x2 equals minus 1. And I also want to consider minus x1 plus 3x2 equals 3. So this system, the two equations here, that's a system. So I would say these are two equations in two unknowns, or you can call them variables, say, right? There's two equations and there's two variables involved. Okay, so that's the basic idea. That's a system of linear equations. That's what we're going to be spending the whole semester on. Now, some important kind of ideas that come along with this. A solution to a system of linear equations. Okay, so that's going to be kind of the name of the game here, is we want to solve these things. And what does it mean to give a solution? Well, this is going to be a list of numbers, and so let me call the list S1 through Sn. You're going to have one for each variable, right? So remember, when I defined my linear equation, I had n variables, and so a solution will be a list of n numbers, and the idea is that those numbers should make, let's say it makes the equations work, So when you plug in, they should be satisfied. And let me just give you an example. So let me go back to that example we had before. x1 minus 2x2 equals minus 1, and it was minus x1 plus 3x2 equals 3. So what's a solution? I claim this has solution, I'm telling you this has solution, let's say 3, 2. Okay? So when I write the solution, right, it's a list of numbers. That first one will be the x1, the second one will be the x2, etc. And how do you check if something is actually a solution? right, you plug in. So let's check this. So that first equation, right, it says if I plug in 3 for x1 minus 2 times 2 for x2, I get minus 1. That's what I should get. And then the other guy should say, well, minus the first number, so minus 3 plus 3 times the second number x2 should equal, yeah, what is that? That's 6 minus 3, that is 3. So that works as well. Okay? So it is indeed a solution. You just checked that, right? It's easy to check if a given list of numbers is a solution. You just plug in. So you just plug in to check. Okay, and so the goal of the course, more or less, is going to be to, if you're given a system of, let's say, m equations in n unknowns, the goal will be to describe all possible solutions. And I should say already that if they exist at all. So we'll see examples where actually there is no solution to such a system. And that'll be the name of the game here. One more piece of terminology here. The solution set of a system is the collection of all solutions to the system. Okay, so in this example, right, this system here had this as a solution, but we don't know if there's others right now. There could be maybe 6, 1 is a solution. You can check that, it won't be, but at this point we don't know actually what the whole story is. Okay, so again, that's a kind of brief introduction of what we're going to be studying. I want to emphasize that there's actually another way to look at this stuff from a geometric perspective. So on the face of it, linear algebra is it's algebraic, it's kind of symbolic, pushing around symbols and numbers. But what's kind of cool about linear algebra is there's actually some geometry hidden in the background that I want to always emphasize. So let me go back to that example. So this is x1 minus 2x2 equals minus 1. This is our running example. Okay, so we know what the solution, we know one solution for this guy that we just looked at. So again, this is 2 equations in 2 unknowns. And just moving forward, I want to emphasize or just get you used to the idea that we're going to be talking in general about m equations in n unknowns. That'll be the convention that we're going to follow. So what I want to point out here is that this actually corresponds to a geometric picture, namely 2 lines in the x1, x2 plane. Okay, so let me show you what I mean by that. So if I take this equation and let me solve for, let's say solve for 2x2, so that's going to be 2x2 equals x1 plus x1 plus 1. So in other words, x2 equals 1/2 x1 plus 1/2, right? So look at that. That's a line, right? So you might be used to y equals mx plus b. We just called the variable something else, right? So x2 equals 1/2 x1 plus 1/2. This is a line with slope 1/2 and y-intercept, or x2-intercept 1/2. The other guy, right, is going to be, 3x2 equals x1 plus 3. In other words, x2 equals 1/3 x1 plus 1. Okay, so that's the other equation. So that's another line. And geometrically what's happening here is you've got, let me draw this x1, x2 plane here. Okay, so these will be 2 lines in the plane. Let me draw, here's x1, here's x2. Let me get a color here. See if I've got a color that'll help me distinguish the 2 lines. Okay, so the first line, let's say the black line here, this is going to be a line with, if that's 1, it'll have y-intercept 1/2 and slope 1/2. So something like this, that's the first line. The second line, let me actually circle in blue. So this will be a line that has y-intercept 1, right, or x2-intercept 1, and slope 1/3. So something like this, that's the second line. And now you see, right, the solution. The solution will be a choice of x1, x2 that satisfies both of these lines. In other words, the intersection. So, it's not quite to scale here, but it looks about 3, 2. So this is, my picture's not precise here, but you can see that it's, something like 3, 2. That's what we saw in the other above. So let me just emphasize that the solution is an intersection point of these two lines. And of course, as you know, if you have two lines in the plane, there will be only one solution if they do intersect. Well, that's not quite true. We'll see in a second what else can happen. Okay, but in this example anyway, we see that there's one solution. Okay, these are not parallel lines. They intersect in one place. Now, what else can happen? So just kind of in this simple example with two equations in two variables, well, I kind of hinted at this already, right? What else can lines do? Well, you can have lines that don't intersect. In other words, they can be parallel, right? So if you have one line like this and the other line like this, if they're parallel, so for instance, if you took, well, I don't know, something like x1 minus 2x2 equals minus 1, and something like minus x1 plus 2x2 equals, say, 3, if you look at those two equations, they'll describe parallel lines. And so what's happening here is you have actually no solution. Okay, so for this system of linear equations, you get no solution because these two parallel lines don't intersect. At the other extreme, kind of a funny thing to think about maybe, but what if you had the black line like this, and then the blue line was actually the same line? Okay, so that can happen. I mean, so for instance, if you had the black line given by this equation, and let's say the blue line is given by something like this, you'll see that this is actually just a negative of that equation. They're going to define the same line. But the point here is that what are the intersection points? Well, you know, this is an intersection point, so is that, so is that, so is that, so is that. Right? There's an infinite number of solutions here. Infinite number of solutions. Okay, and so that's the other extreme. You can have, well, you know, there's kind of three things that can happen. One solution when the two lines intersect in the usual way. No solution when they're parallel. An infinite number of solutions when they're actually the same line. And what I want to just mention now as we close is that this little example is actually the story for all systems. So here's the important fact that I'll end with, that I want to, you know, we'll see this throughout the semester, is that any system of linear equations, three things can happen. So let me just say m linear equations in n unknowns. I want to emphasize, you know, that this is a general story. If you have m equations in n unknowns, so like 40 equations in 22 unknowns, this can have those three things happen. So you can have either no solution, in which case we say that the system is inconsistent. It can have one unique solution, so just a single solution. Or you can have an infinite number of solutions. Infinitely many solutions. And I just want to say that, well, so inconsistent is when you have no solution, and both of these are when you say it's consistent. Okay, so if you have one or infinitely many, it's called a consistent system. But what I want to emphasize here is that you can never have just 42 solutions, right? If you have more than one solution to a system, you must have an infinitely many solutions. Okay, and so that's kind of a observation I want to make now. It's going to run throughout the course, and we'll see that kind of over and over again, but I just want to kind of mention it on day one here. Okay, so we'll continue with more systems next time. See you then.